What if AI could not only answer your questions, but also think its way to the solution, like a detective piecing together clues? Or what if we could turbocharge scientific discovery, making breakthroughs faster and more efficiently than ever before? That's the kind of cutting-edge stuff we're diving into today on AI by AI.
Exactly. We've got a packed agenda, exploring some seriously cool advancements. First up, we're breaking down self-give, a new way to give large language models associative thinking skills. Think of it like teaching an AI to connect the dots between different ideas, especially when it comes to complex scientific questions.
Then, we're shifting gears to PiFlow, a framework that's revolutionizing scientific discovery by treating it like a puzzle of uncertainty. It helps AI agents explore new ideas while still sticking to established scientific principles. It's all about finding that sweet spot between what we know and what we could know.
After that, we're tackling the tricky world of optimizing AI models, specifically the ADAM algorithm. We'll unpack a new theoretical analysis that explains how ADAM converges, even in the messy, non-smooth landscapes of deep learning. Don't worry, we'll keep it simple. Think of it as understanding how your GPS finds the best route, even with unexpected detours.
Next, we're shrinking things down with DLISC, a clever technique for running powerful language models on your phone or other devices. It's all about making AI more accessible and efficient, even when you don't have a supercomputer at your fingertips.
Finally, we're exploring how to use AI to create more AI. We'll be discussing a study that uses LLMs to generate synthetic data for improving machine translation, especially for languages that don't have a lot of resources. It's like teaching a language model to teach itself, opening up new possibilities for global communication. So buckle up. It's going to be a fascinating ride.
Okay, let's dive into this paper on self-give. The title is Self-Give, Associative Thinking from Limited Structured Knowledge for Enhanced Large Language Model Reasoning. It's all about improving how LLMs reason, especially when they don't have all the info they need.
So the core idea is associative thinking, right? Like how we connect different pieces of information to solve problems. The paper mentions melatonin and insomnia as an example. How does self-give actually implement this in LLMs?
Exactly. The paper highlights that LLMs, like humans, need to connect existing knowledge to new questions, especially in science. Self-give. Self-give is a framework that helps LLMs do this automatically using reinforcement learning. It extracts structured information and entity sets to link to the concepts in the query.
Got it. So it's not just about feeding the LLM more data, but about helping it make connections between the data it already has and the question at hand. What's the difference between self-give and the previous method, give?
Good question. Give, or graph-inspired veracity extrapolation, uses a knowledge graph to extrapolate structured knowledge, but it creates and prunes a lot of hypothetical triplets, which is inefficient. Self-give addresses this by being more efficient and generalizable. It reduces the number of LLM calls, works better on smaller LLMs, and avoids inaccurate knowledge from LLM pruning.
So self-give is like a streamlined version of give. The paper mentions significant performance improvements on biomedical QA tasks. Can you give me some specific numbers?
Absolutely. When fine-tuned with a small knowledge graph, self-give improved the performance of Quen 2.5, 3B, and 7B models significantly. For example, the 3B model jumped from 28% to 71.4%, and the 7B model went from 78.6% to 90.5% on unseen samples. Plus, the 7B model matched or outperformed GPT-3.5 Turbo with Jive while using way fewer tokens.
Wow, those are impressive gains. So, smaller models can achieve comparable or even better performance than larger models with the original give method. What's the secret sauce? How does self-give actually work?
The key is in how it uses structured knowledge. Instead of relying on long texts like traditional RAG systems, SelfGive uses KG triplets, which are more concise. These triplets provide a framework for sequential reasoning, helping the LLM solve problems more like a human expert. The paper also emphasizes that SelfGive doesn't explicitly construct extrapolated knowledge or supervise the association process. The LLM learns to use the retrieved structured knowledge and related entities independently through reinforcement learning.
Okay, so it's learning to connect the dots on its own. The paper mentions entity groups and KG triplets. Can you break that down a bit more?
Sure. SelfGive first identifies relevant KG triplets by forming relevant entity groups and deducing the cross-group KG connections. Think of entity groups as collections of similar concepts. For example, if the query is about melatonin, the entity group might include other hormones or sleep aids. Then it retrieves KG triplets that connect these groups, helping the LLM to extrapolate relationships between the queried concepts.
So it's like building a mini knowledge graph around the query. How does reinforcement learning come into play?
The LLM is optimized using GRPO, which rewards accuracy in reasoning format. It's motivated to use the expert triplets and entity groups correctly. This helps the model learn to associate the limited structured knowledge with the query, enhancing its performance in those challenging scientific QA tasks.
That makes sense. So it's a combination of structured knowledge retrieval and reinforcement learning to teach the LLM how to think associatively. The paper also talks about the limitations of LLMs in knowledge-intensive tasks. Why do LLMs struggle with these tasks?
LLMs acquire reasoning ability through pre-training and reinforcement learning. However, they often encounter unsolvable issues within a single forward pass, especially when they need new knowledge. Even with increasing pre-training, their reasoning abilities are constrained when facing problems requiring external information, which is common in fields like biomedicine and healthcare.
So they need a little help from external knowledge sources. The paper compares SelfGive to other methods like RAG and TUG. How does it stack up?
SelfGive consistently outperforms baseline techniques in various QA tasks. It surpasses methods like K-shot prompting, RAG, and TUG. The key is that SelfGive effectively allows LLMs to associate limited structured knowledge with queries, avoiding hallucinations without direct gold context. It also allows smaller models to match or exceed the performance of agentic retrieval reasoning approaches on larger models like GPT 3.5T.
That's a big deal. So it's not just about accuracy, but also about efficiency. How does SelfGive reduce token usage compared to other methods?
SelfGive achieves better performance while reducing token usage by more than 90%. This is because agentic frameworks require iterative interactions with LLMs using complex instructions, leading to more model calls. SelfGive simplifies the process with fewer LLM calls, incorporating only the query, knowledge, and entity groups in the context.
Okay, so it's more efficient in terms of both computation and token usage. The paper also mentions ablation studies. What did those reveal?
The ablation studies examined the sensitivity of SelfGive to the number of additional entities per group. It turns out that SelfGive performs optimally with a suitable number of extra entities. Too few, and there aren't enough KG triplets to build associations. Too many and irrelevant triplets cause hallucinations. There's also an analysis of information gain per entity group, showing that both sparse and dense information gain can negatively impact performance.
So there's a sweet spot in terms of the amount of information provided. What are the limitations of SelfGive?
One limitation is the lack of explicit supervision on the reasoning process. While SelfGive improves QA accuracy, there's no guarantee of correct knowledge utilization or faithfulness of the reasoning chain. Also, SelfGive involves additional training costs compared to inference-time agentic frameworks. Finally, there's a risk of overfitting due to the binary accuracy signal and a lack of universally optimal hyperparameters across datasets.
Okay, so there's room for improvement in terms of reasoning transparency and training efficiency. Overall, it sounds like SelfGive is a promising approach for enhancing LLM reasoning in knowledge-intensive tasks. It's more efficient, generalizable, and effective than previous methods, especially for smaller models.
All right, let's dive into this paper. PiFlow Principle-Aware Scientific Discovery with Multi-Agent Collaboration. It's all about using AI to speed up scientific breakthroughs, which is pretty exciting.
Definitely. I've seen a lot of buzz around using large language models or LLMs in scientific research. But this paper seems to be addressing some key limitations of current approaches. What's the core problem they're tackling?
So the authors point out that existing LLM-based systems often use predefined workflows, which can lead to aimless hypothesizing. Basically, the AI is generating ideas without a clear direction or a strong connection to actual scientific principles. They also struggle to link hypotheses to supporting evidence, making it hard to systematically reduce uncertainty.
That makes sense. It's like the AI is throwing ideas at the wall without really understanding the underlying science. So how does PiFlow address this?
PiFlow introduces an information theoretical framework that treats scientific discovery as a structured problem of reducing uncertainty. It's guided by scientific principles like established laws or patterns in a specific field. Think of it as giving the AI a compass and a map, instead of just letting it wander randomly.
Okay, so it's not just about generating hypotheses, but also about strategically selecting which principles to focus on. How does it decide which principles are most promising?
That's where the min-max optimization comes in. PiFlow tries to minimize cumulative regret, which means exploiting known high-potential principles. At the same time, it maximizes information gain, which encourages exploring new hypotheses. It's a balancing act between sticking with what works and venturing into the unknown.
Interesting. So cumulative regret is basically the cost of not choosing the best option, and information gain is how much we learn from trying something new. How does PiFlow actually implement this in practice?
PiFlow is designed as a plug-and-play module that can be integrated with existing multi-agent systems or MAS. These MAS typically have agents that handle hypothesizing and experimentation. PiFlow uses scientific principles which can be proposed or refined by LLMs to steer the exploration process.
So it's like adding a strategic layer on top of existing AI systems. It sounds like it could be pretty versatile. What kind of scientific domains did they test it on?
They evaluated PiFlow across 3 different areas, discovering nanomaterial structures, biomolecules, and superconductor candidates with specific properties. In all 3, it significantly improved discovery efficiency and solution quality compared to a vanilla agent system.
That's a pretty diverse set of applications. Can you give me some specific numbers on the performance improvements?
Sure. They measured performance using 2 metrics, area under the curve, AUC, and solution quality, SQ. PiFlow showed a 73.55% increase, which reflects how quickly it finds good solutions, and a 94.06% improvement in SQ, which measures the quality of the final solution.
Wow, those are some impressive gains. So AUC is about efficiency, and SQ is about the end result. It sounds like PiFlow is both faster and better at finding solutions. But what about the role of large language models in all of this? How do they fit into the PiFlow framework?
LLMs are used in a couple of key ways. First, they can help propose initial scientific principles to guide the exploration. Second, they're used within the hypothesis agent to generate testable hypotheses based on those principles. However, the paper emphasizes that PiFlow helps to overcome the hallucinations or biases that LLMs can sometimes introduce.
So PiFlow helps to ground the LLM's reasoning in actual scientific principles, making the whole process more reliable. It's like having a knowledgeable supervisor overseeing the AI's work. What about the theoretical guarantees they mention?
They prove that PiFlow achieves cumulative regret growth of OLT over T exploration steps. This sublinear regret means that the system's efficiency is guaranteed even in complex discovery landscapes. In simpler terms, it's mathematically proven to be efficient.
Okay, that's reassuring. It's good to know there's a theoretical foundation behind the practical results. So what are the key takeaways from this paper?
The main takeaway is that PiFlow offers a new paradigm for principle-aware scientific discovery. It's a plug-and-play framework that can be integrated with existing MAS to enhance exploration and exploitation, leading to significant improvements in discovery efficiency and operational flexibility. It's all about making AI-driven research more robust and accelerated.
It sounds like a really promising approach. By focusing on scientific principles and structured uncertainty reduction, PiFlow could help us unlock new discoveries in a wide range of fields. I'm curious to see how it evolves and gets applied in the future.
Okay, let's dive into this paper on atoms' convergence in deep ReLU networks. It's a pretty dense theoretical piece, but the core idea is super relevant. Understanding why ATOM, a popular optimization algorithm, works so well in training these networks, even though the math is kinda messy.
Right? ATOM's like the go-to optimizer for a lot of deep learning tasks. But the theory's always lagged behind the practice, especially with ReLU networks. What's the big challenge there?
The main issue is that ReLU, or rectified linear unit, activations create these piecewise linear loss landscapes. Imagine a surface made of flat planes all stitched together. That means standard smoothness assumptions, which a lot of optimization theory relies on, just don't hold. It's like trying to use calculus on something that's not even differentiable everywhere.
So no nice smooth curves for the algorithm to follow, just a bunch of sharp corners and edges. How do they even begin to tackle that?
They use some pretty advanced math, including stratified Morse theory and something called Kakeya sets. Stratified Morse theory helps analyze the loss landscape by breaking it down into smaller, manageable pieces, or strata. It's like saying, okay, the whole thing is messy, but let's look at each flat piece individually.
And what about these Kakeya sets? That sounds wild.
Kakeya sets are these weird mathematical objects that contain a line segment in every direction. The authors use them to get a handle on how well the optimization explores the parameter space. It's about ensuring that ATOM doesn't just get stuck in one corner of the landscape, but actually searches in all relevant directions.
Okay, so they're using these tools to prove that ATOM actually converges to a good solution, even in this non-smooth setting. What's their main result?
They derive a generalization bound for ATOM in deep ReLU networks and the first global optimal convergence for ATOM in the non-smooth, non-convex ReLU landscape without a global PL or convexity assumption. Basically, they show that ATOM can find the global minimum of the loss function even without assuming the loss landscape is nice and smooth or convex.
That's a pretty big deal. So what are the key insights that make this possible?
Two main things. First, they show that even though a ReLU network creates exponentially many regions, a well-behaved optimizer only visits a polynomial number of them. Second, they prove a uniform low barrier, ULB, property. This means there aren't any huge walls or barriers in the loss landscape that would prevent the optimizer from moving between different regions.
A uniform low barrier property. So it's like saying the landscape is connected in a way that the optimizer can actually navigate it without getting stuck behind some massive wall.
Exactly. They combine this ULB property with a detailed analysis of how many regions the optimizer crosses, refining their analysis through things like margin-based stability, adaptive spectral floors, and low-rank drift. It's a multi-layered approach to really nail down the behavior of ATOM.
Okay, so they're not just saying ATOM converges, but they're also giving us a sense of how it converges, and what properties of the network and the optimizer make that possible. What are some of the specific contributions they highlight?
They point out several key contributions. First, the global convergence guarantees for ATOM without relying on smoothness or convexity assumptions. Second, a framework that reduces the complexity of region crossings from exponential to near linear. Third, that uniform low barrier property we talked about. And finally, they combine ULB with something called a local KL inequality to show a two-phase convergence, a sublinear phase followed by exponential descent.
A two-phase convergence. So it's like ATOM starts off exploring the landscape, and then once it finds a good area, it zooms in for the final descent.
Precisely. They also extend their analysis to handle more realistic scenarios, like losses that aren't perfectly smooth, adversarial attacks, and data that isn't perfectly independent. It's about showing that their results are robust and applicable in practice.
That's great. It's one thing to have a theoretical result, but it's another to show that it holds up when things get messy in the real world. So what are some of the assumptions they make to get these results?
They assume things like bounded layer norms, regional smoothness within each activation cone, and a specific step size schedule for the learning rate. They also introduce several empirically motivated assumptions about the optimization behavior, like L1 margin-based cutoff, L2 spectral floor of atom second moment, L3 low-rank gradients and sparsity, L4 sparse tope bound, L5 sub-Gaussian drift control, L6 angular concentration, and L7 directional richness.
Those sound like they're trying to capture what actually happens during training, rather than just making simplifying assumptions for the math. Can you break down a couple of those?
Sure. L1, the margin-based cutoff, says that ReLU activations develop a stability margin after initial training. Basically, the network pushes parameters away from the decision boundaries, so activations become more stable. L2, the spectral floor, assumes that atom second moment estimates have a lower bound. This prevents the algorithm from taking excessively large steps in certain directions.
Okay, so L1 is about stabilizing the network, and L2 is about controlling the step size. What about L3, low-rank gradients and sparsity?
That one says that gradients lie in a low-dimensional subspace, and at most K-ReLUs activate per input. This reflects the empirical observation that training often happens in a much smaller subspace than the full parameter space. And L4, the sparse tope bound, says that at most K neurons are active per input, and only K neurons are active across all training. This captures the inherent sparsity of ReLU activations.
So they're using these assumptions to show that the optimization process is actually much simpler than it might seem at first glance. How do these assumptions help them bound the number of region crossings?
They start with the exponential worst-case bound from stratified Morse theory, and then incrementally apply these assumptions to get a tighter bound. Each assumption corresponds to a real-world phenomenon observed in deep learning, making the theory more relevant. For example, the margin cutoff reduces the number of crossings by limiting the time window where activations can change. The spectral floor ensures finite trajectory length, and the low-rank drift reduces the dimensionality of the problem.
It's like they're peeling back the layers of complexity, one assumption at a time, to reveal the underlying structure of the optimization process. What's the final result of this region crossing analysis?
They show that the number of crossings is bounded by OFF poly log n log df, where df is the effective dimension and n is the number of ReLU boundaries. This is a huge improvement over the exponential bound from stratified Morse theory.
That's a massive reduction in complexity. So with this finite region bound in hand, how do they prove convergence and generalization?
They prove two main statements. First, that atom converges under finite crossings, driving the gradient norm to zero at a certain rate and then enjoying linear descent inside the final cone. Second, they use the Kakia-based generalization argument to show that the test train gap is of order O squared dfs log on delta ha n.
Okay, so they're showing that atom not only converges to a good solution, but also generalizes well to unseen data. How does the Kakia set come into play here?
The Kakia set argument is used to show that after the activation masks freeze, the optimization path sweeps every direction in the effective subspace. This directional richness is then converted into a generalization bound using a covering number argument.
So it's about ensuring that the optimizer explores the parameter space sufficiently to avoid overfitting. What's the overall picture of atom's convergence that emerges from this analysis?
They describe a two-phase process. In phase 1, atom crosses at most OF log n activation hyperplanes, driving the gradient norm to zero at a rate of O1 for squirt t. In phase 2, once the masks freeze, the loss satisfies a low Krutikowa-Yashevich inequality, giving geometric loss decay.
And this KL inequality is what guarantees the exponential convergence in the final phase.
Exactly. They also show that under a mild uniform low barrier connectivity assumption, every cone-wise minimum has the same loss value, so atom converges to a global minimizer.
That ULB assumption seems crucial for guaranteeing global optimality. What happens if that assumption doesn't hold?
If the ULB assumption doesn't hold, atom might get stuck in a local minimum. but their analysis still provides guarantees about convergence to a cone-wise minimum and generalization within that region.
Okay, so even in the worst case, they're providing some useful guarantees. How does their generalization bound compare to other bounds in the literature?
They claim that their Kakeya-based bound outperforms standard pack-based bounds by replacing global norm dependencies with a much smaller effective dimension and requiring non-TK or convexity assumptions. This yields tighter test-train gap bounds in high-dimensional settings.
That's a significant advantage. So what are some of the practical implications of this work? Any advice for tuning Atom in ReLU networks?
They offer several concrete suggestions. Use default knobs like beta 1 equals 0.9, beta 2 equals 0.99 to 0.999, and epsilon equals 10 to 6. Use a base step size of 10 to 3 for small nets or 10 to 4 for very deep nets. Track the ReLU sign flip rate and raise the learning rate slightly or move to a 1t or cosine decay when it drops below 1%. Set V0 equals epsilon to create a spectral floor. Use L2 decay to bias updates toward top PCs, shrinking the effective dimension. Use larger batches to yield sub-Gaussian gradient noise, and project recent gradients onto random vectors to ensure directional coverage.
That's some really practical advice. It's great to see theoretical work that actually translates into actionable insights for practitioners. What are some of the limitations of this work, and what future directions do they suggest?
They acknowledge that they've validated their refinements on image classification models and would like to extend empirical validation into RL settings. They also suggest extending the analysis to architectures that mix ReLU, GU, and attention softmaxes, studying the stratified Morse view of the landscape, tracking the dynamic effective dimension, generalizing the Kakeya covering bound to curved manifolds, proving that the uniform low barrier property implies mode connectivity tunnels and scaling to LLMs.
Those are some ambitious goals. It sounds like there's still a lot of work to be done in understanding the optimization landscape of deep neural networks. What's the overall takeaway from this paper?
The main takeaway is that Atom and related adaptive optimizers enjoy global convergence to a true optimum, driven by a data-driven refinement framework that collapses region-crossing complexity and a Kakeya-based generalization bound. This demystifies the empirical success of adaptive methods and shows that practical training phenomena ensure both efficient global optimization and tight generalization guarantees. All right, let's dive into this paper. Effective and efficient schema-aware information extraction using on-device large language models. It's all about making information extraction, or IE, work better on devices like phones or embedded systems, where resources are limited.
IE is key for turning unstructured text into structured knowledge, right? Like pulling entities, relationships, and events from articles. So what's the big challenge they're tackling here?
Exactly. The challenge is that large language models, or LLMs, which are great at IE, are computationally intensive. Putting them on devices leads to problems like hallucinations, where the model makes stuff up, limited context length, and slow processing times, especially when dealing with lots of different extraction schemas.
Skiing the blueprints for what kind of information we're trying to extract, like person, organization, or event type, right?
Spot on. So to solve this, they're proposing something called Dual-LoRA with Incremental Schema Caching, or DLISC. It's a two-stage approach designed specifically for on-device LLMs.
Dual-LoRA. Sounds interesting. What's LoRA in this context?
LoRA stands for low-rank adaptation. It's a way to fine-tune a pre-trained LLM with only a small number of extra parameters. Think of it as adding a small, efficient module to the LLM that's specific to the IE task instead of retraining the entire massive model. This is crucial for on-device applications.
Okay, so Dual-LoRA means they're using two of these LoRA modules. What's the purpose of each?
Precisely. The first, the identification LoRA, is responsible for figuring out which schemas are most relevant to the input text. The second, the extraction LoRA, then uses those schemas to actually extract the information. It's like having one module that says, okay, this text is about a company acquisition, and another that says, great, let's extract the names of the companies, the date, and the amount of money involved.
That makes sense. So it's a divide and conquer strategy. What about this incremental schema caching part? How does that speed things up?
That's where the efficiency comes in. Incremental schema caching, or ISC, is like a memory for the model. It stores schemas that have already been used, so if the same schema is needed again, the model can just grab it from the cache instead of recomputing it. It's similar to how your computer caches frequently accessed data to make things faster.
Ah, so it avoids redundant calculations. Smart. So the paper compares against other methods. What were the baselines and how did DLISC perform?
They compare DLISC against retrieval augmented generation, or RAG baselines. RAG is a popular approach where you retrieve relevant information from an external knowledge source to help the LLM generate better results. The baselines use different retrieval methods like BM25, BGE Reranker v2m3, and LLM embedder.
BM25 is a classic information retrieval algorithm, right? And the others are more recent embedding-based methods.
Exactly. BM25 is a probabilistic retrieval function that weights terms based on frequency and document length. The other two use embeddings to represent text and find similar documents. The results showed that DLISC consistently outperformed these RAG baselines in terms of F1 score, which measures the overall quality of the information extraction.
And what about efficiency? Did the caching actually make a difference?
Big time. They measured the average extraction time per sample, and DLISC with incremental schema caching significantly reduced latency compared to Dual-LoRA without caching. So the caching strategy is definitely paying off in terms of speed.
They also did an ablation study, right, to see how much each part of DLISC contributes.
Yep. They looked at the identification and extraction phases separately. The results showed that DLISC achieved the highest precision in the identification phase and the highest F1 score in the extraction phase, confirming that both components are working well together.
So overall, DLISC seems like a promising approach for on-device information extraction. What are some of the limitations they mention?
Good question. They point out that they only used LoRa adapters, and it's unclear if the approach would generalize to other types of adapters. Also, they couldn't deploy on real edge devices due to resource constraints, and their current implementation doesn't handle multilingual scenarios well.
Those are definitely important areas for future work. It would be interesting to see how DLISC performs on a wider range of devices and languages. Thanks for the breakdown.
All right, let's dive into this paper on scaling low-resource machine translation using synthetic data generated by large language models. It's a hot topic, and this research brings some interesting insights.
Definitely. Low-resource MT is a huge challenge. We've seen incredible progress in translating between languages like English and Spanish, but what about languages with limited data? That's where this synthetic data approach comes in, right?
Exactly. The core idea is to use LLMs like GPT-4o in this case to generate parallel data, that is, translated sentence pairs, for these low-resource languages. Think of it as creating artificial training data where real data is scarce.
So they're essentially teaching the machine translation system with data that's been invented by another AI. Sounds a bit risky. How do they ensure the quality of this synthetic data?
That's the million-dollar question. The researchers tackled this in a few ways. First, they started with a well-defined document-level corpus, the English Europarl, which is derived from European Parliament proceedings. This gives them a good, consistent source text.
Ah, so they're not just randomly generating text. They're translating existing, relatively high-quality English text into the target languages.
Precisely. Then they used GPT-4o to translate this Europarl data into 7 diverse low-resource languages: Basque, Scottish Gaelic, Icelandic, Georgian, Macedonian, Somali, and Ukrainian. They chose these languages carefully, based on a preliminary experiment to see which ones GPT-4o could handle reasonably well.
Okay, that makes sense. So they're not just blindly throwing data at the problem, they're being selective about the languages and using a structured source text. What about the actual translation process? How did they prompt GPT-4o?
They used a pretty straightforward prompt, instructing the model to provide the translation in the correct script and explicitly telling it not to include any extra explanations or text. They wanted just the translation, clean and simple.
Got it. But even with a good prompt, LLMs can be a bit creative. Did they do any post-processing to clean up the data?
Absolutely. They had a few key steps. First, they segmented the translated paragraphs into individual sentences. Then they used a language identifier to filter out any sentences that weren't actually in the target language, a common issue with LLMs, which sometimes hallucinate and produce text in the wrong language.
So a language identifier is like a gatekeeper, making sure only the correct language gets through. Smart. What else did they do?
Finally, they aligned the clean target sentences with their original English counterparts, preserving the document structure. This is crucial for maintaining the parallel nature of the data.
Okay, so they've got this synthetic parallel corpus. But how do they know if it's any good? Did they just trust GPT-4o's output?
No way. They did both automatic and human evaluations. For automatic evaluation, they used metrics like BiCleaner AI and Comet Kiwi. BiCleaner AI is a binary classifier that determines if two sentences are valid translations of each other, while Comet Kiwi is a quality estimation metric that predicts human judgment scores.
So BiCleaner AI is like a quick check for whether the sentences are even related, and Comet Kiwi gives a more nuanced quality score. What did these metrics tell them?
Generally, the metrics showed that the data was of high quality, especially for Ukrainian and Macedonian. However, they also noticed lower quality for languages like Scottish Gaelic, Somali, and Georgian.
That makes sense. Some languages are just harder for LLMs to handle than others. But automatic metrics are just one piece of the puzzle, right? What about human evaluation?
Exactly. They had native speakers evaluate a subset of the data, assigning scores based on meaning, preservation, fluency, and naturalness. This is a more subjective but also more reliable way to assess the quality.
And what did the humans say?
The human evaluation largely confirmed the automatic metrics. Macedonian and Ukrainian were rated highly, while Georgian showed considerably lower quality. Interestingly, they also found that BiCleaner AI sometimes underestimated the quality of high-quality translations.
That's a good reminder that even the best automatic metrics aren't perfect. So they've got a synthetic corpus, they've evaluated its quality. Now the big question, does it actually improve machine translation performance?
That's what they tested next. They trained and fine-tuned various MT models on this synthetic data and compared their performance to models trained on other data or no data at all.
What kind of models did they use?
They experimented with a few different architectures, including a transformer-based model trained from scratch, Opus MT models, which are pre-trained multilingual models, NLLB200, another large multilingual model, and even LMA3B, a general-purpose LLM.
Okay, so a good mix of translation-specific models and a more general LLM. What were the key findings?
First, they found that even a small model trained solely on the synthetic data could achieve strong baseline performance, sometimes even surpassing larger models like NLLB and LLama for certain languages. This shows that the synthetic data is rich enough to train functional MT systems without any external pre-training.
That's impressive. So even if the data isn't perfect, it's still valuable for getting a basic translation system up and running. What about fine-tuning pre-trained models?
Fine-tuning consistently improved NLLB, confirming that the synthetic data is well suited for adapting these models to low-resource languages. However, they also found that for some languages, like Macedonian and Ukrainian, fine-tuning Opus MT actually hurt performance. This suggests that when there's already enough real data available, the synthetic data can sometimes lead to overfitting.
So there's a sweet spot. The synthetic data is most useful when real data is scarce, but it can be detrimental when there's already a decent amount of real data. What about Llama? How did a general-purpose LLM perform?
Llama initially struggled, reflecting its lack of inherent translation capability. While fine-tuning improved its performance significantly, it still underperformed smaller translation-specific models. This suggests that while synthetic data can help adapt a general-purpose LLM, it can't fully compensate for the mismatch between the model's architecture and the translation task.
That's a key takeaway. Translation-specific models are still more efficient for translation even with synthetic data. Did they compare their synthetic data to existing real-world data?
Yes, they compared their data to HPLTV2, a parallel corpus derived from web sources. They found that their synthetic data performed comparably to HPLT, and even better, that combining the two datasets yielded the best overall performance. This suggests that the synthetic data introduces useful diversity and complements the real-world data.
So it's not just a replacement for real data, it can actually enhance it. That's a powerful finding. They also mentioned something about pivoting. What's that about?
Because they started with the English Europarl corpus, which is multi-parallel across many languages, they could use English as a pivot, create synthetic translations between other language pairs. For example, they could translate from Finnish to Somali by first translating Finnish to English and then English to Somali, all using their synthetic data.
So they're leveraging the multilinguality of the original corpus to create even more synthetic data. Did they test this pivoting approach?
They did. They found that fine-tuning Opus MT on this pivoted data significantly improved Finnish-Somali translation, highlighting the utility of synthetic data for non-English-centric translation.
That's great. It shows that this approach can be used to create translation systems for language pairs that don't even involve English. Finally, they mentioned something called SynOPUS. What's that?
SynOPUS is a new public repository for synthetic parallel datasets. They created it to promote reproducibility, transparency, and reuse of synthetic data. They're inviting the community to contribute their own datasets, which is a fantastic initiative.
Definitely. Sharing resources is crucial for advancing research in this area. So overall, what are the key takeaways from this paper?
The main takeaway is that LLM-generated synthetic data, even when noisy, can be a valuable resource for low-resource machine translation. It can be used to train competitive MT models from scratch, consistently improve pre-trained systems, and complement existing real-world data. However, it's important to be mindful of the quality of the data, the choice of model architecture, and the potential for overfitting.
Right? It's not a magic bullet, but it's a powerful tool that can help bridge the gap for languages with limited resources. It'll be interesting to see how this field evolves as LLMs become even more powerful and data generation techniques become more sophisticated.
Well, that was quite the journey through the AI landscape. From teaching models to think associatively and accelerating scientific discovery, to understanding the inner workings of optimization algorithms and shrinking AI for on-device use, it's clear how rapidly the field is evolving.
Absolutely. It's fascinating to see how researchers are pushing the boundaries, not just in terms of scale, but also in terms of efficiency and accessibility. That idea of using AI to create more AI, especially for bridging language gaps, really highlights the potential for democratizing access to information.
And it's not just about building bigger and better models. It's about understanding why they work. Like that deep dive into atoms convergence, that kind of theoretical work is crucial for building trust and ensuring that these systems are reliable and robust.
Definitely. And the focus on making AI more efficient so it can run on our phones and other devices is a game changer. It opens up so many possibilities for real-world applications, from personalized healthcare to on-the-go language translation.
It really feels like we're entering a new era where AI is becoming more integrated into our daily lives, helping us solve complex problems and unlock new discoveries. Who knows what breakthroughs are just around the corner?
Exactly. It's an exciting time to be following these advancements. Thanks for joining us on this exploration, and we'll catch you next time with more AI by AI.